introduction. So I will show you now the validation results of the axle block acceleration measurement. This was done in two places in Romania, in Fareu test ring and in the line Bartolomeu Sarnesti. So first I will introduce what is axle block acceleration, and then I'm going to show you those two examples in the test ring and in the regional line Bartolomeu Sarnesti. So what is this innovation about? We install accelerometers in the axle block of the train so that whenever a wheel is passing over a defect, the vibration will be detected, and then we can detect, we can find from small defects, like the one that you see in the picture over there, squats, or also bigger defects. So far, we have tested this technology before in the Netherlands with our CTO train, and then we installed it in Fareu and in Bartolomeu Sarnesti in the NeTIRail project. So this is how the signal is gonna look like. You see over there a very small defect that I see a squat. It's very small. Some of them, they even disappear due to natural wear. And over there, you see the vibrations, the accelerometers, acceleration signals. Then in the part over here, you see what it's in the vertical direction. And in the part over there, you see the longitudinal direction. In the case of a small defects, they are easier to be detected in the longitudinal direction. And then we get vibrations. In this case, the defect was quite isolated, so we could even see it from the time domain signals, the vibration signals. You see a peak over there, then okay, something's going on here. But in cases when we have also other assets, the switches, some welds, some joints, then to differentiate those peaks, then we analyze in the frequency domain what are the frequency components. So you're gonna see the analysis both the time domain signals, but they mainly focus on what is the frequency content. So that's the case of a small defect, and here a very severe defect. And then here it's quite obvious from the time domain signal and the energy level. It's excited in the same frequency band as the small ones here, but they are more prominent, the amount of energy that we're getting here. So the first campaign, well, this was done in the test rig of Affair. This was done in October 2017. The test ring is the one that you see over there, and that's the map that you see. And then over here are the detection results. You see in the marks the different locations that were interesting for monitoring. We found, of course, the insulated joints. We found also the switches that are over there, because then we have a different vibrations, energy. And we covered also the rest of the rail, and we found in total 17 defects. Most of them were wheel burns. And we locate them, we did the mapping, and then later with the colleagues of Affair, we went to visit the whole test rig, so to validate what we found were there. Luckily, everything was there. And we also covered to see if there were other small defects in the way, and then we couldn't find it. So now I'm going to show you some examples. So, I forgot also to mention. So the system was installed in a train, and we test different speeds. So we went from 20 kilometers in terms of 20 kilometers per hour. So it was 20, 40, 60, then we reached 120 kilometers per hour. That is the conventional speed in the Netherlands, and we are used to measure at that speed. But then in the test rig, for the first time, we could reach even 200, 220 kilometers per hour. That's already, we could say, it's a high-speed measurement. So for all those defects, then we could analyze the trends. And now I'm going to show you just some few examples of what was obtained. So there are these kind of defects that are small wheel burns. And over here, you see the signals. This is wheel burn that was detected with a measurement at 80 kilometers per hour. So this is what we are more or less used to. And you see over there the time domain peaks, also the frequency domain that get decided in the other frequencies. Preliminary over here. This doesn't mean that here you don't get also excitations. It's just that they are not as prominent as in the defect. So this is how it looks like at 80 kilometers per hour. And here, this is how it looks like the same defect at 200 kilometers per hour. Then, because of the energy, because of the high speed, it seems like, and this is what is more or less the proof, that the system is better as the train goes faster. So more energy, it's a small, although it was very small defect, generates that strong acceleration. That means there's a lot of dynamic forces happening there, and a high speed in the test ring, because it's tested usually at high speed, then yeah, it's important to take care of the critical defects. And let me see. So I will show you, if I have time at the end of the presentation, some videos of how we were recording the measurements. So here, well, the conclusion is that it was possible to cover from 20 kilometers up to 220 kilometers per hour a defect detection methodology. The next test, this was conducted in Romania, in Transylvania, and this was performed in September 2016, Bartolomeo Sarnesti, and then here's the team. Again, the same system was installed. In this case, from our experience, the first time that we could do it in a train that was in operation with actual passengers getting on board. So we didn't take much picture of this, but then you see that the cyclists getting inside, and the proof that there were people that were not from our team using the train. And then Jan Morales over there, the technician that was taking the measurements. So this was we are very happy about getting this sort of data, because eventually this kind of technology, the best is to install it in operational trains. Then you don't need to book a special measurement train for getting all sort of information. Still, there are many challenges with this sort of measurements. We have drastic variations of the speeds, so it's not continuous as what's in the test ring, but then we have acceleration, deacceleration, areas where we can get good information. And here I put that like a question mark for error, because from the measurements in the test ring, then in test ring, we can fit the detections per different speeds, and then we can make use not only the areas that are sort of more or less constant, but we can also cover from 20 kilometers and so on. When the train is fully stopped at zero, there's no energy, we cannot see much of defects. So that the lowest area we cannot use, but the highest we can. There are other challenges, like in the region where we took the measurement, the GPS somehow was not as accurate as we used to have it in the Netherlands. But nevertheless, the detections, then later the partners from RCCF, they went to validate some of the results. So we could detect from the small defects to the more severe ones. In this case, because it was the first time trying it in a operational condition, we set a ranking of the top 75 places where we found the highest variations, and then the partners they validate, and they found different situations that were happening at those locations. We also analyzed the wells that are in these railways. So although from the pictures you see that the three wells, they look more or less similar, from the top of the view there are not an evident defect happening. With this system, we can analyze the energy. And the one over here, the well number 7, has the highest level of energy. That means that in case that you need to do a replacement, I don't know, you need to rank which of the wells you would like later to repair. The well number 7, it will be the one that should have the highest priority because the highest dynamic forces are happening there. And so this is one of the analyses we could do. And also there was a corrugated rail. In this case, it was not short pitch corrugation, but it had a longer wavelength. And this could be detected in the range of around 200 hertz. But it's the area that you see over here, the peaks over there. All right, so conclusions. And am I on time? Yes. Okay. So in the Netherlands and Romania, the detection of different defects was possible, and with the NeTIRail, we could claim now that it was possible to detect also defects in other countries, not just in Netherlands. That helps for the generalization purposes. The detailed information of the small defects is very important for the grinding operations. The smaller the defects, then the more effective is the grinding. If you wait for defects to grow, the cracks, and so on, then no matter the grinding you pass, the defect will remain and will reappear again. Then it makes no sense to grind in that part. So you can get the mapping of where those small defects are detected and optimize grinding. Also, you can get the map of where the moderate and severe defects are located, and you can rank them as well. So you can plan the local replacement operations based on where the highest dynamic forces are happening. From Fareo testing ring, we could cover the responses of wells, wheel burns, switches and crossing an insulated joint from 20 up to 220 kilometers per hour. That means that the technology might be applicable for metros, conventional, and high-speed railways. In the case of metros, maybe we will have to face some problems with the GPS location, but as far as we have access to the tacho of the train or the positioning system of the train, then we could manage to get an estimation of the location of the defects. Finally, during operation, in a train near Brasov, we could also gather all sort of information, and that means that then this technology can also be applicable in operational trains. Further research is going to focus on online detection of defects, so to make the algorithms to run even faster, because right now we're collecting a lot of information, it's a lot of data that is very difficult to process online, so everything we have done so far is offline, but we are near there, so, and yeah, that was thanks to the project. And also we claim that this sort of system gives you information, but to have the complete picture of what's happening in the railways, you need also other sources of information. Sometimes images can tell you something that is visible. In this case, you can also validate, let's say, but also in the railways are happening things below the rail, in the fastening system, in the sleeper, things that you cannot see easily. And then the system can provide information about that. So we think that the fusion of ABA, image, ultrasonic, eddy current, and other measurements will be the next step that we want to do some research, because then it will be much more strong, the picture that we get about what's happening in the track. So thanks for your attention. And
do you want to do a video?
Can I do it?